Welcome back, students. Welcome to another edition of Mr. Bessling's videos with their awkward jokes and full of all of their awkward moments. Don't worry, there's plenty more to come. So today's video starts Chapter 7, and Chapter 7 is a big turning point. In this section, we will learn hypothesis testing. Now, this video is designed purely as an instruction, and I'm going to work through a hypothesis test. Later, we will actually have later videos that will actually have more problems in them. But for this one, I just want you to kind of relax and watch me work through a problem and do a hypothesis test and test a claim that I think you should be able to understand. You're actually not going to be doing any calculations in this video. So again, the objectives of this video are pretty much just to learn the structure of a hypothesis test, and we'll get into more details later. The rest of the class, from Chapter 7 on to Chapter 10, we will be doing nothing but different hypothesis tests. So it's really important that you understand the basic nature, the basic reasoning, and what could possibly go wrong in a hypothesis test. And we're going to understand things like, well, again, these things will all come, but after today's lesson, you will definitely need to learn how to write the null and alternative hypotheses. Excuse me, a few things went wrong on this video, but I just want to reiterate that for this video, and in fact, section 7.1, there's no calculating really involved. It's really just understanding how to set these things up. Section 7.2, 7.3, 7.4, 7.5, we'll get more into calculating. Oh, see there, I erased number 2. That's why I was like, yes, no calculations are required yet. Okay, so let's look into what a hypothesis test. You guys are all doing hypothesis tests for your projects, and you might not know it yet. But a hypothesis test, what a hypothesis does is it tests the validity of a claim using a random sample from the population. So there's plenty of claims that we could make out there. This car gets 35 miles per gallon. That's a claim. What other claims could you think of? Michael Jordan shoots 30% free three-point shots, if we didn't know that already. We could make claims like, hey, boys are taller than girls on average. And that brings me to just a good point. When I say something like boys are taller than girls, we know that that there's plenty of girls who are taller than boys and vice versa. So if we say something like boys are taller than girls, we actually need to be a little bit more careful what we say. All boys are not taller than all girls. But it's certainly reasonable to say the average height of boys is taller than the average height of girls. So that's one thing we need to be we need to take in consideration as we do these hypothesis tests. What am I actually testing? I don't test that boys are taller than girls. It's a general statement. I can't really test that, or I could just say it's false because I know at least one girl who's taller than one boy. But I could definitely make the claim that the average height of boys is taller than the average heights of girls. And then I could say something like boys are taller than girls on average. Yeah. Okay, and like I was kind of mentioning here is that we make a test about a parameter using a statistic. The idea is we're trying to do inferential statistics. We're trying to use a sample to make a general statement about the population. We're going to learn how to do different kinds of hypothesis tests. We're going to learn how to do tests for means, proportions, and also variances. For instance, like the mean height, like means, for instance, I could make the claim that boys on average are taller than girls. I could maybe test a proportion, like maybe it's known that 3% of widgets at Clumsy Core are defective. After some changes, we want to test to see if this defect rate has improved. Is it less than 3%? We could test variances, and that one gets a little sneaky, but it's more useful testing variances in what we call ANOVA multiple samples, kind of like, hey, which out of all three of these different baseball bats, which one hits the farthest? Okay, so this one you do want to realize, you want to write this down here, that a hypothesis test consists of all these different things here. Number one, a null and alternative hypothesis. That's going to be our objective today, to learn how to write those. A random sample from the population. A check of conditions. We have to make sure that we are able to use the methods that we are learning. We have to be able to, we're going to learn how to calculate our test statistic and p-value. That name p-value is going to come up over and over and over again, and if you ask any adult who's taken a statistics course, they probably remember something about the p-value. What's your p-value? What's your p-value? Well, based on that p-value, we make a decision, and from that decision, we get to draw a conclusion, if we can draw a conclusion. Okay, so let's work through this problem here. Okay, it is known that IQ scores follow a normal distribution with a mean of 100 and a standard deviation of 15. We claim that our school has a higher mean IQ score, and higher than 100, that is, because we think the students at our school are really smart. So we randomly sample 25 students, and that yields a mean IQ score of 107. Is there convincing evidence to suggest that students at our school have a higher mean GPA? And I know what you're thinking already. Well, yeah, dude, we just sampled 25 people, and they had a mean of 107. That's way higher than the average of 100. But remember, if we just sample, like, let's just say one person randomly out of the population, again, let me put it this way. Let me do this on the next screen here. Let's suppose that the IQ scores follows a normal distribution, and this is the population, so this is one person, the mean of 100, and a standard deviation of 15. Oops, that was supposed to be a 15. There, now it's 15. So you can imagine adding a couple standard deviations to the right, a couple standard deviations to the left. And what you see now is, if you just chose one person at random from the population, there's a pretty good chance just that they're going to have a IQ over 107. There could be people out there with IQs of 130, even down to 70. So we might go, well, yeah, 107, that is clearly over 100. But the idea is, could that have just been purely caused by random chance? Like, just by pure random chance, maybe it was true that at our school the IQ scores still have a mean of 100, but just randomly, we just got, a few smart people by random chance. Maybe we just, happened randomly to get a few geniuses in there, and not enough, say people with weaker IQs to balance that out. And that's the question we're going to be answering essentially. What if our school had a mean of 100, the IQ of 100, could this have happened by random chance, getting a mean of 107, or is there something really there? Are students indeed, do they have a higher average? Maybe the real average is like 107 indeed. Maybe that's the real average of IQ scores at our school. Not to say that means that it's going to be exactly 107, but is it 100 or is it greater? Okay, so let's work through this here, and again, just relax. So one of the first things we learn, and we do in a hypothesis test, is we write our hypotheses. And we have two hypotheses. Again, we will formally define these in the minute. We have the null hypothesis, which we often call HO. So this is the null. And we have the alternative, which we either call HA or H1. I'll be honest, I like to write, your book uses HA. I like to use H1 only because sometimes an A to me looks like an O and it's hard to tell which one's which. So your book calls it HA. I'll be calling it H1 because, especially with the stylist, my A's might look too much like O's. So this is called the alternative hypothesis, also HA. Ha! Oh, right. Okay, so for this hypothesis, this is going to be my null hypothesis. And this is always the nature of a hypothesis test. I'm going to assume the null hypothesis that our school has a mean of 100. And I'm actually not trying to show that the null hypothesis is true. I'm going to try to show that my alternative hypothesis is true. So the alternative hypothesis in this case is really going to be the claim that I'm trying to make. What am I trying to make? I'm trying to make the claim that my school has a mean over 100. So I write my alternative that my mean is over 100. And I apologize, I'm going to rewrite my my null hypothesis. I'm rewriting my null hypothesis that the mean is less than or equal to 100. And let me explain here, again, just for a second here. We're going to assume, again, when we do hypothesis testing, that the actual mean or proportion is under the null hypothesis is true. So the idea is we're going to assume that that the average IQ score at our school is 100 until we have enough evidence to suggest otherwise. And notice that I write that the null could be equal or less than 100, because let's just put it this way: if I sampled my school and randomly sampled and they had a sample mean of 97, case closed, right? I'm not going to be able to prove my point that the mean IQ score is greater than 100. I mean, I kind of have to have a sample mean over in this case, over the mean that I am trying to test. Okay, so this is going to be my hypotheses, and it's always a good idea to write out what your parameter is. That is, what do I mean by this letter mu right now? Where mu is the true, or it's the true mean IQ score of my school. And notice something. I already know what the true population mean is of everyone in the population, if the population is all people. That was given to me to begin with. That was 100 with a standard deviation of 15. But I'm not trying to test that claim. I'm trying to test, is my school essentially smarter than average? That is, do they have a higher average IQ score? So this is why it's a good idea to write down what your parameter is. And again, what do I mean by parameter? I mean, when I use this letter mu, what does it mean? I'm also going to set what I call a significance level, alpha, And let me just briefly explain what alpha is. We've been talking throughout this course, is this an unusual event? And a lot of students kind of ask, well, what does that mean? Like, how low of a probability does something have to be for us to call it unusual? And I think I typically said, oh, 5%, 10%, sometimes 1%. Well, this is what we're going to get at, is this number alpha. And we're pretty much going to set this number alpha, also called the significance level, at typically 10, 5, or 1%. So that is 0.10, 0.05, or 0.01. And what this represents is this little tail here on the right. That's kind of like, well, how unusually high would my sample mean have to be in order for me to kind of go, well, that's so unusual that probably wouldn't happen by random chance. And typically, we will use that cutoff at 5%. Sometimes 10%, sometimes 1%. There's benefits of having it higher. There's benefits of having it lower that we'll see later in the courses. Okay, so that's my hypotheses. The next part I want to do is check my conditions. And my conditions for this class are pretty much just two things, and you've seen these before. Number one, is my sample random? If my sample's not random, it's not a representation of the population, and I can't do any kind of inference from a bias sample about the population. Can't do it. Number two is going to be our normal condition that we just saw last chapter. And in this case, my normal condition was met. This is going to end up being a z-test like we're going to do in 7.2. This is going to be a z-test because I was given the standard deviation. I was told to assume that the standard deviation is 15. But in this case, it's normal because my population is already normal to begin with. And we'll go through all those conditions as we go along. Okay, the next part is what we call the test statistics. So now let's look at this here. This is where things really start coming together. In Chapter 5, we learned what was called the sampling distribution of X bar. And we said, and this is if we take a sample from a population with a known mean, and we can calculate the standard deviation of likely outcomes of other means. So, and whenever we do these sampling distributions, we assume that the null hypothesis is true. So that is, my mean is supposed to be 100, because that's the average IQ score. I sampled 25 people. The standard deviation of the population is known as 15. So what I want to do now is calculate, if you remember this guy, the standard deviation of the sampling distribution of X bar. And this was the standard deviation of the population divided by the square root of n. So in that case, for this example, the standard deviation of the population was 15, and the sample size was 25. So that's going to be 15 over 5. That's going to equal 3. I'm going to move to the next screen and again tell you what this all describes. So what that sampling distribution describes is all likely samples from this population, where the mean is 100, we sampled 25 people, and the standard deviation of the population was 15, and that meant that this number that we'd calculated before, the standard deviation of the sampling distribution is 3. So let's add a couple standard deviations. 106. There's one standard deviation, two standard deviations. I'll take one or two away. Okay, so this bell curve right now describes the likely samples I would get the likely sample means, that is, the likely averages from samples of 25 people from the population with a mean of 100 and a standard deviation of 15. So again, it helps to kind of, using the empirical rule, it helps to look at this. That is, if it were true that, at least at my school, that the mean was 100 and that the standard deviation was 15, and we're going to assume that the standard deviation is 15, then if I'm sampling 25 people, about 68% of the time, the average from that sample, the sample mean, should be between 97 and 103. And 95% of the time should be plus or minus 2 standard deviations. So 95% of the time, it should be between 106 and 94. So here's what we got. We did this. We took a random sample, and we supposedly got an average of 107. So what we want to know is, clearly that's unusually high, and the question is, what's the probability of getting a result this high or higher? Because 107 is unusual, 108 would be unusual, and anything above 107 in this case would be unusual. And that's going to be what we're going to be calling the p-value. So if we look here, how many standard deviations is this guy from the mean? We'll take a z-score, and this z-score is going to be what's going to be our what we're going to be calling later down the line the test statistic. So we had our sample was 107. That was our sample mean. The mean of the population is supposed to be 100. And the standard deviation of this ended up being the standard deviation of the population divided by the square root of the sample size. So in that case, that's going to be 7 over 3, or 2.33. So this is going to be what we're going to be calling our test statistic. And in this case, our observation, 107, our sample mean, the average IQ between 25 people, was 2.33 standard deviations above where I would expect it to be if the null hypothesis was true, if the true average of IQ students is actually 100. So the next thing I'm going to do is going to go, okay, 2.3 standard deviations, that's pretty far. That's pretty unusual. Well, exactly how unusual is it? I will just use this z-score now to find the probability of getting a z-score this high or higher. And I'll use my normal table in the back. And since it's a right-sided probability, I have to find the I have to 1 minus the probability that's on my chart. And what's on my chart at 2.33? I got 0.9901. So this is going to be 0.001. Excuse me, 0.0099, or essentially 0.99%, just about 1%. Okay, so let's go back here. This, what I just calculated, is going to be really what my p-value is, and that is my p-value in this case, 0.0099. Okay, so what this means, my p-value in this case being 0.0099, if it were true that IQ scores at my school had an average of 100, then the probability of me getting a sample this big, that is 107 or bigger, is 0.99%. So now I have a decision to make. I'm going to be making my decision, and there's going to be 2 decisions. And my decision is going to be either, do I reject the null hypothesis? That is, do I reject that the mean is 100? Or do I fail to reject the null hypothesis? And when I say fail to reject Notice that I don't say except, and that's going to be very important. This is very much like our United States trial by jury. I either say somebody's guilty or not guilty. I don't say that they're innocent. I pretty much say that I don't have enough evidence to show that they're guilty. They could be innocent, they could still be guilty, but I just cannot show it beyond a reasonable doubt. And it brings me to something else. Notice how I never said the word prove in here. Statistics, we don't prove anything, and I want to very much warn you on that. I don't ever want to see the word prove or hear the word prove in statistics, because we typically don't prove anything. We just show things are very unlikely to occur by random chance, therefore most likely false. Okay, so in this case, going back to my decision, my p-value was 0.0099. Do I reject the null or fail to reject the null? Well, I use that value that I had said before, this number alpha, that significance. I kind of said, how unusual does something have to be? And I drew that cutoff at 5%. Well, the probability of my sample occurring by random chance, if the null hypothesis is true, was less than 1%. And I drew the cutoff at 5%. So in this case, my decision is I reject the null hypothesis. And typically, this is what we want to do in statistics. Often, it is our case to try to reject the null hypothesis. So what we're usually in a statistics test for is not to show that the null hypothesis is true. We don't do that ever. Even if we fail to reject the null hypothesis, we do not say the null hypothesis is true. We're usually in this to reject the null hypothesis. So I reject the null hypothesis because my p-value was lower than my significance level. And now let's make my conclusion. So if I reject the null hypothesis, this is my decision. I'm essentially going to be choosing one or the other. And if I said no to you, that means yay to you. Well, what's yay to you? That the average JSARIS IQ is over 100. So typically I would say something like that, like this. There is convincing evidence that the true IQ score at my school is over 100. Notice I didn't say what value it was. I could create a confidence interval and give you a reasonable estimate of what it is. And I guarantee you, if I did at least a 99% confidence interval, that the number 100 would not be in my confidence interval as well. There's a big link between hypothesis testing and confidence intervals. So this is the nature of a hypothesis test. Let's run through this just one last time. We're going to be doing lots of these, so I didn't expect you to make a ton of sense with this, but we're going to get practice. I start with a hypothesis, and I always assume that the null hypothesis is true. And we'll practice writing our hypotheses next. I check my conditions. I need to make sure that my population is random, and this normal condition, when I say this normal condition, it doesn't mean that the population is normal. What it means is down here, what we learned in chapter 5, that the sampling distribution of x bar is normal, or when we get there later, p hat, proportions. And what that means is that the distribution of sample means of whatever size sample, in this case 25, is normal. Not that the population is necessarily normal, but we learned that if the population is normal, it doesn't matter what the sample size is, the distribution of sample means is going to be normal as well. And that's usually where we're going to need this equation. You're going to see this equation come up, or if we don't know the standard deviation, we use the sample standard deviation to find that value. We'll get to that one in 7.3. Okay, and again, we assume the null hypothesis is true, and from that we calculate what we call a test statistic, and the test statistic ended up being the z-score that I calculated, 2.33. That is, it's 2.33 standard deviations above the mean, my sample mean. And I'm saying again, the likely samples of, the likely means of 25 people. And now I found my this value, the probability of getting a result this extreme. This is going to be our p-value. And then ultimately we make a decision. We either reject the null hypothesis, which is usually kind of our point to begin with. And if we reject the null hypothesis, we reject it in favor of the alternative hypothesis. Or else we fail to reject the null hypothesis. And that doesn't mean that the null hypothesis is true. That just means that we did not show enough evidence that it's false. Think not guilty over innocent. Okay, I hope you liked that. I didn't like it much either. Okay.